Hi all, today we discuss some theorems on Riemann-Stieltjes integral. So we start discussing theorem 6.4 first. This, the statement of theorem is if P star is a refinement of P. You already seen what is the refinement. Then the lower sum LP f alpha, which is less than or equal to LP star f alpha, and in case of upper sum that decreases UP star f alpha, UP star f alpha is less than or equal to UP f alpha. So these are the two inequalities relating this upper sum, Riemann-Stieltjes sum and Riemann-Stieltjes lower sums. Okay, so we prove this. First of all, we define what is a refinement. If we have a partition like this is our interval AB, and we have a partition x1, x2 and so on. Finally we have xn, and this is our x0. So if this is the partition P, the refinement means P star is a superset of this P. So in fact this P is a set x0, x1, etc., xn with these properties. The partition should have two properties. The first property is x0 will be A, comma xn will be B, and the second property will be this x0 less than x1 less than or equal to, both will be the same, etc., less than or equal to xn. Okay, if P is a partition with these properties, or P is a set of points with these properties, then P star is said to be a refinement of P if P star contains that P. Okay, so this is the definition of the refinement. That means if you take a partition P of AB, then if you insert at least one point here, then you can get a refinement. Okay, if you put a C here, then you can say that this the new set of points x0, x1, C, x2, etc. Will make a refinement of this P. Okay, so if you choose any refinement of P, then lower sum increases and upper sum decreases. Okay, so this is the theorem. So to prove this theorem, we if you can insert x star here instead of, see, I put x star here, that is a refinement, and if you put another point x double star here, then that will also a set of all these points form a refinement of P as well. Okay, because this P star, that refinement contains two extra points than this points of P. So you can insert any finite number of points inside this interval that will make a refinement of P. So we prove this theorem by taking a refinement P star of P, including one point to this P. Okay, so we start with the partition, this partition P, and we insert at exactly one point first. Okay, so from this P, how do you get P star? P star will be P union the extra point x star. Okay, so this is the P star. So this x star, since x star is a point of this P star, that will be in some of the subintervals of P. So we name it as xi minus 1 xi. If we choose such subinterval, then x star is assumed to be here. Okay, so in this case, our interval xi minus 1 xi will be divided into two subintervals again, that is xi minus 1 x star. This will be one such subinterval, and the other part will be x star comma xi. So this is the second part of the subinterval. So if we consider P star, then we need to consider two subintervals instead of this xi minus 1 xi. So we define the maximum value or infimum value of this f of x not maximum, infimum value of f of x in this interval is denoted by w1, and w2 is the infimum of f of x in this interval. That means x belongs to x star xi. Here x belongs to xi minus 1 x star. So this is the case. Now we can easily say that this w1 is always greater than or equal to mi, and w2 is also greater than or equal to mi. This is because this is a subset of xi minus 1 xi. Okay, if a is subset of b, then infimum, this is the subset. So infimum, what is the relationship between infimum a and infimum b? Okay, so subset should have larger infimum. So this is the idea we have used here. So please try to show that this if a is less than b, a is contained in b, then infimum a is greater than or equal to infimum b. So this is the result we have used here. Therefore w1 is greater than or equal to mi, and w2 is greater than or equal to mi as well. Now you consider the sum. What is LP star f alpha minus LP f alpha? Okay, so if you consider this difference, so as far as this xi minus 1 xi is not concerned, all the other terms will be the same. Okay, in these two sums. Okay, so the remaining will be, in the difference of this, the remaining will be w1 alpha of x star minus alpha of xi minus 1 plus w2 times alpha xi minus alpha of x star minus small mi times alpha of xi minus alpha of xi minus 1. So these are the two unequal terms in these two sums. In the first sum we have the sum in the first lower sum we will have this w1 times this plus w2 times this, and in the second lower sum, this LP f alpha, we have this term. So we cannot cancel these two terms, so that's why this present here, all other terms will be cancelled each other. So this can be written as this is w1 minus mi into alpha x star minus alpha xi minus 1 plus w2 minus mi alpha xi minus alpha x star. Okay, this is because you need to insert one term to this sum. Okay, here we have this alpha w1 times x star minus x alpha of x star minus alpha of xi minus 1, but we never have this small mi times this. Okay, so we need to add and subtract one terms to this. Okay, so similarly the only thing remaining here is, first of all, you need to expand this bracket w1 times alpha of x star minus w1 times alpha of xi minus 1 plus open all these brackets and insert one term and negative of that. Then you can easily regroup these terms in this manner, or otherwise you can check this expression and open all the brackets and you will get this one. Okay, so we can just verify for this. We have w1 times this is already always here, and w2 times this is always here. Okay, but the only thing, what is the remaining thing? Minus mi times this. Okay, minus mi times this bracket means minus mi times this term and minus mi times this term. Okay, so that is plus mi times alpha of xi minus 1, that is already here. Okay, so this is minus mi times this is the foreign term in this sum, and similarly when you observe this one, you know that w2 times this bracket is already there, and minus mi times alpha of xi, that is here minus mi times alpha of xi. So the foreign term will be the product of these two, minus mi times minus alpha x star. Okay, so that is the negative of this term. Okay, so this is the foreign term here and this is the foreign term here, so these two terms can be cancelled. Okay, so you will get this the previous sum. So you need to insert minus mi times alpha of x star and plus mi times alpha of x star. So you need to insert these two terms to this sum, then you can regroup like this. Okay, so what is the advantage of this? This is always greater than or equal to 0, because we have already seen that this w1 is greater than or equal to mi and w2 is greater than or equal to mi, so these two brackets are always non-negative. Then you consider this one. Okay, since x star, what is x star? X star is here, so alpha is increasing, so alpha of x star is greater than or equal to alpha of xi minus 1, so this is also non-negative. Similarly, this bracket is also non-negative, so all these terms are non-negative terms, so you can get this LP star f alpha is greater than or equal to LP f alpha. Okay, so this proves the one inequality of the theorem. Okay, in the similar fashion you can use the property of the supremum before that you need to if you have one extra points than this points of p, you can this much terms. Okay, if you insert two more points to this p, then there will be two such interval. Okay, so you have this bracket plus you have the same bracket corresponding to the other interval as well. Okay, so that will be present in this. So anyway, you can get this is always greater than or equal to 0. So whenever you insert an n number of points to this partition, you can get this much terms n times. Okay, though all those terms will be non-negative, so the sum is also non-negative. So you can easily prove this result for any refinement. Okay, refinement is obtained by any number inserted by the refinement is obtained by inserting any number of terms to this p. You can get the same result. Okay, so now you use the property of the supremum. If a is greater than a subset of b, then supremum of a is always greater than less than or equal to supremum of b. Okay, using this fact you can easily prove that the upper sum gets reduced. That means if capital Wi is capital W1 is the supremum corresponding to the subinterval, so we have this result, capital Mi and capital W2 is less than or equal to capital Mi. So using these inequalities, you can easily prove that UP star f alpha is always less than or equal to UP f alpha. Okay, so this proves theorem 6.4. Next we have theorem 6.5. So lower Riemann Stieltjes integral is always less than or equal to upper Riemann Stieltjes integral. So this we will prove this theorem by taking two arbitrary partitions P1 and P2 be two arbitrary partitions. There is no relation between these two partitions. Two arbitrary partitions of AB. Okay, that means you can vary this partition P1 independent of this partition P2, and similarly the other way you can vary this P2 without affecting the partition P1. Okay, so if this is the case, then you define P is equal to P1 union P2. Okay, so or P star is equal to P1 union P2 is the partition, and from this you can get P star is contained P star is the union of these two, so P star contains P1 and P star contains P2 as well. Okay, so P star can be considered as a common refinement of both the partition P1 and P2. Okay, now we use the previous result. LP1 F alpha is always less than or equal to LP star F alpha. Okay, so this is because P1 is P star is a refinement of P1. Okay, now we know that this is lower sum, and that is always greater. This is always less than or equal to P star F alpha. Okay, we know that LP F alpha is nothing but the summation I equal to 1 to n small mi delta alpha. So this is the definition of lower sum, and this is always less than or equal to summation I equal to 1 to n capital Mi delta alpha, because capital Mi is the infimum of f of x, and capital Mi is the supremum of f of x in the same interval. So this Mi is always less than or equal to capital Mi. Now you can get this one. So this is all, which is nothing but upper Riemann-Schiller's sum. Okay, so we can say that for any arbitrary partition P, LPF alpha is always less than or equal to UPF alpha. Okay, so here we have LP star F alpha is less than or equal to UP star F alpha, which is less than or equal to UP2 F alpha. Clear? Because P2 P star is a refinement of P2 as well. Now we combine first and last term, we can get LP1 F alpha less than or equal to UP2 F alpha. Okay, now take supremum P1 varies over set over P of AB, LP1 F alpha less than or equal to UP2 F alpha. There is no change. If you take the supremum varying P1, that will never change this. Okay, so that will same as UP2 F alpha. Then this implies, what is this? This is lower integral a to b f d alpha less than or equal to UP2 F alpha. Now take the supremum and infimum over all partition P2 belongs to P of AB. Okay, so this will be that will implies integral, that will implies integral a to b, lower integral a to b f d alpha less than or equal to infimum P2 belongs to P of AB. P2 belongs to P of AB, U P2 F alpha. Okay, so this implies integral lower integral a to b f d alpha is same as less than or equal to, so not same, less than or equal to integral upper integral a to b f d alpha. Okay, so this proves theorem 6.5. Okay, in the next class we will discuss sufficient and necessary and sufficient condition for the integrability, Riemann-Schiller's integrability of function. Okay, thank you.